chapter. I changed the order of chapters. Chapter 10 is now Wolfram. Okay, who is Stephen Wolfram? I hope you know him. He is one of those super genius people. He entered Oxford at 17 and left. Anyways, he got his PhD at 1980, so how much? 21 years old, yes. And his thesis committee was composed of Feynman and others. Okay, worked independently, published a widely cited paper on heavy quark production at age 18. At age 15, began research on applied quantum field theory. Then he went on to this new avenue. So he wrote this book in 2002. It's called A New Kind of Science. And it's really, really valuable. This book is really, really valuable for its perspective. Okay, the perspective is this. Actually, we mentioned this perspective already. Computational universe. There is this universe, and then there is computational universe. There are some mappings between them. So the way Wolfram looks at it is that I can use. He built Mathematica, right? Do you know the software Mathematica? So he says that he really says this in the book, that just like Galileo built a telescope and looked at this universe, I am going to use Mathematica as a telescope, and I'm going to look at the computational universe to see what I can find there. Okay? So we will start with a very simple, but maybe the most important thing in this book, which is elementary cellular automata. Okay? So let's talk about elementary cellular automata. I don't have my picture here. There you go. So what is elementary cellular automata? Let's start by talking about automaton. Automaton is the singular of automata. Okay? An automaton, the way that we are going to see it is basically, you can think of a square grid, like composed of some values. And for example, sand pile model was an automaton. Okay, there were some values, and those values were changing according to some rule, right? So in general, these kinds of stuff are called automatons. So some rule, and you get new values. Let me just, like you add 1 and it becomes 2. And when it's 4, it tuples, etc. There's some rule. So elementary cellular automata, really, it is showing the way that Wolfram was seeing this. So here's the idea. You start with a string of numbers, string of zeros and ones, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, etc. Okay? In the elementary version, what happens to this state is determined by these 3 values, okay, in the elementary version. So you need a rule. right? How many possible states do we have here? How many different possibilities we can have in those 3 boxes? 8 possibilities, right? Could be 0, 0, 0, 0, 0, 1, etc. 8 possibilities. And your rule is supposed to map that state to either 0 or 1, right? So you have 8 possibilities, and each one of those possibilities can be mapped to either 0 or 1. How many, exactly, how many possible rules there can be? Let me write all those 8 possibilities: 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0. So your rule could be mapping all of them to 0, right? Or it can be mapping one of them to 1, etc., right? So how many possible rules are there? 2 to the 8, yes. 2 to the power of 8, which is 256 rules. Okay? So you get, let me tell you. So did you understand this part? Like there can be 8 possibilities for 3 states. Yes? So I'm going to generate a rule. Let's say my first rule, actually my 0th rule, is this. Everything goes to 0. That's rule number 0. Let's make this one 1. Everything goes to 0 except when it's 0, 0, 0. Then it's rule number 1. Then this is 0, this is 1. Rule number 2. And if you continue this, you can go all the way up to 255. So you go from 0 to 255. That's actually how Wolfram names this stuff. For example, if you have 1, 1, so you multiply this one with 1, this one with 2, this one with 4, this one with 8, this one with 16, this one with 32, this one with 64, this one with 128, right? So let's get the rule 30, which is very, very famous. Is this rule 30? No. What do we need to make rule 30? We need 16. Then do we need 8?
1, 1, 1, 0. We need 1, 1, 1, 0. Sorry. 1, 1, 0, 1.
This is 0? This is correct? This is correct. Right? 16 plus 8 plus 4 plus 2 is 30. Yes? Are you with me? Yes. So this is rule 30, for example. So
I thought you said rule 30.
Sorry. 30. Yes, 30. Very good. So do you see why it fits so nicely with Wolfram's idea? Because there are only 256 of them. We have all the time to look at each one of them very closely, right? So let's write a program that will generate them, and let's look at them one by one.
What is the 1, 2, 4, 8, 16? What is that?
Just 2 to the 0, 2 to the 0, 2 to the 1, so that it's binary, so that we don't mix them. Alrighty. Yes.
I don't understand the motivation of choosing only like 3 bits at the beginning.
Say it again. What?
Choosing only the 3 bits.
Why only the 3? Simplest possible approach.
So this rule was only valid for
So like let's apply rule 30. Let's apply rule 30 to this particular initial state. Okay. So we go to here, what do we have? 0, 1, 1. We look at the table, 0, 1, 1 goes to 1. So what do we write? We write 1 here. Okay? We look at here, 1, 1, 0. We look at the table, 1, 1, 0 goes to 0. We write here 0. Does it make sense? What are we going to do about this one? Periodic boundary condition. We assume that this is over here. So 1, 0, 1. Does it make sense? 1, 0, 1 goes to 0. There you go, 0. Okay? Exactly. So let's look at this program. What this program is doing, it starts with some number of cells. Let's start nice and easy with 20 cells. And we are going to run for 10 time steps. So 20 here, 10 here. Okay? So this is space, this is time. Then we write a rule. Let's start with rule number 0. And we format it into binary stuff. Then we make integers out of that. Then we start with a state. The initial state could be random or could be all zeros except in the middle there could be 1. Then there is this line that does all the heavy lifting. So what's going on here? Let me first describe this part. This part transfers. So let's say, let me just copy this from here. Copy, paste it here. So how do I decide what will happen to this green area? I can do it in the following way. I can shift it to the left. Okay. Oh, too much shifting. Shift it 1 to the left, 1 to the right. Okay. And as you can see, I get the, oops, anyways. This one is the same as that rectangle, right? Yes? Yes. So I multiply this one with 2 to the 2, this one with 2 to the 1, this one with 2 to the 0, all the rows. That way, I get the relevant value for this one. For this one, 0, 1, 0 corresponds to 2. Then I go to here. Where is 2? So, give me a moment. 0, 1, 2, 3, 4, 5, 6, 7. 2 is here, so I apply that rule. Okay? Never mind, it's coding, right? You can figure it out. Why do we have 7 minus that value, bits? Because it's not starting from 0, 0, 0. I mean, it's not going this way, but it's going this way. Never mind. You get it. Let's just run the code. We have the widget. We have everything. Let's run the code. Rule number 0. Do you agree that rule number 0 should be like this? Because everything is mapped to 0. Even if I start from random initial condition, it will immediately stop, right? Because everything is mapped to 0. What was rule number 1? Rule number 1 is the rule when it maps to 1 when, no, rule number 1. What is rule number 1?
Well, John, I kind of don't get what we're supposed to see. Like, what are we supposed to understand from that?
Very good. Very good.
This is one if there's for rule number 1.
Yeah, but why it's not 1 here? Okay. I'm telling you. So, look at this one. This is the initial condition, okay? Rule number 1 tells you that you get 1 only if you have 0, 0, 0. Yes? So, we get 1 only in this middle part, 0, 0, 0. Okay? We get 1. Otherwise, we get zeros everywhere else, right? Are you with me?
Yes.
Then 0, 1, 0 creates this 0, and there is also 0 here, there is also 0 here. So you create this pattern.
So this black box indicates 1.
Yeah.
Yeah.
So let's run this rule for longer times with. You see, this rule just creates these objects. Okay? Very good. If I start with simpler initial condition, it just have this one. Okay? Now let's take our telescope to a ride. Okay, we have our telescope. Let's look at all the rules. So this is rule number 0. Starting from 1, just goes to. This is rule number 1, right?
Yeah.
Rule number 2. Rule number 3. Rule number 4. Numero 6, 7, 8, 10, 11, 12, 13, 14. Seems to be boring, right?
That's because we started to avoid initial states.
Oh no.
I mean, didn't we just start?
Yes. But it will be a lot of fun even with this boring initial state. Just hang in there. Coming soon. 16, 17, 18. The good old fragrance from once upon a time, right? But this is just starting. 19, 20, 21, 22. This is a different Sierpinski triangle. This 18 has these branches. The one with 22 has these Tetris figures. Do you see? 22, 23, 24, 25, 26, another Sierpinski, 27, 28, 29, 30. That's where all the hell breaks loose. We start with very simple condition, very simple initial condition, just zeros and just 1, but we create this ordered, disordered mess. How can that be? Let me just go back here and write rule 30 and go all the way. Okay, so in the rule 30 you have this ordered side to the left. Okay, something ordered on the left, but highly chaotic stuff going on over here to the right. Okay, something very, very peculiar discovered by the telescope. For example, I mean, any scientist's intuition who hasn't seen this before would be to say that you are missing something. That's what Richard Feynman told Wolfram when he, the greatest puzzle solver, right? Richard Feynman, solve this puzzle. I get 0, 0, 0, 0, 1, 0, 0, 0, 0. I have this rule 30, no magic, and you get this one. The mystery of rule 30 is still unresolved, and the main mystery is this. What you create in the middle passes all kinds of pseudo-randomness tests. So you are creating a perfect pseudo-random number generator. You have a perfect pseudorandom number generator with a very simple rule. Okay? Actually, if you want to make $30,000, there is a $30,000 price to anyone who can find what's going to happen here with doing less computations than needed. Does it make sense? If you can computationally reduce, that's the right word. So rule 30 is computationally irreducible for all that we know. No one has ever achieved reducing it. Okay? If you can do it, you get $30,000 and a big thank you from Wolfram. So far, so good. But we are not done. We can continue. Let's switch to random initial condition. Do we have random initial condition here? Yes, we do. So if I go to rule 30, as you can see, some of those rules that seem to be boring gets less boring when you have random initial conditions. 30, now chaos everywhere, right? 31, 32, 33, 34, 35, 37. Something interesting was about to happen but couldn't happen. Order got its way. 40, 41, very interesting but eventually settles down. 42, 43, 44, 45, very interesting. Seems to be chaotic. Seems to be as interesting as rule 30 maybe. 47, 54, coming soon, 53 and 54. Now this one is extra interesting. Yes, it is chaotic, but it has a lot of order as well. As you can see, there are these orbits, stable orbits going, and then they are interacting with things that coming from sides, and they are creating logic. Probably it's Turing complete, but no one have shown this before, I guess. And yes. No. The thing with rule 30 is it's too chaotic to build anything. I mean, any information that you want to send is quickly dissipated into chaos, okay? But you can send some messages downstream with rule 54. Like this is a message, and then it's interacting with a message that's coming from here. I hope I'm making sense. If we'll look at maybe in a greater scale, rule 54. Okay, let's look at it here. Rule 54 and start with random initial conditions. And then let's... Do you see there is this information flow between these things? You can do some algebra there, but this is not the favorite one of, oops. This is not Wolfram's favorite one. His favorite one is on the top of the book. We are coming to the favorite one. 55, 56, let me go back to maybe nice numbers, maybe. So you get a bunch of other Sierpinski triangles. So for example, rule 86, what is it? Can you tell me?
It's like a reverse rule 30.
Exactly. So every rule has its mirror symmetry and then complementary symmetry. Complementary symmetry means that I think we have it at 135 or somewhere. Do you see? Complementary symmetry is when zeros become 1, 1 becomes 0. Okay, very well. And 146, I think, is, no, 47, 48, 49, is the one with mirror complementary symmetry. Do you see it? Mirror and complement. Some rules are complementary symmetries of themselves. Some rules are mirror symmetries of themselves. Some rules are complementary and mirror symmetries of themselves. If you take those ones out, take them out, like gather them together, then you have 88 unique rules. Yes? So if I count 30, 86, 135, and 149 as one rule, then we have 88 of them, not 64. Why would it be 64 if you are not careful? You would think that every rule has its mirror complementary and mirror complementary, but sometimes its mirror is itself. So 1, 2, 3, 4, 5. Very good. Very, very good. Okay. Wolfram's favorite one is 110. Yeah. The one and only. Doesn't seem like anything right now, maybe, but let's look at it here. Let's set it to 110. And you can see that, by the way, you can see that this is the thing on the top of the book. Like, where is it? This is the thing, okay? You can see these complex propagators. It's clearer than rule 54. Rule 54 also has this property of more or less like fields in between, complicated fields. What do we have as fields here? We have these patterns. They are everywhere. This comprises a field, and inside that field, there are these propagators. So this is the field, this is the field, this is something moving in the field, right? But the fact that this field is complicated makes their propagators complicated. Also, the fact that the propagators are complicated makes their interactions complicated and interesting. But if there are too many propagators, then there is a traffic jam, you can't send information. Rule 110 was shown to be Turing complete. You remember the Turing complete stuff? Like you can do any kind of computation with this rule. Do you want to compute rule 110 with rule 110? Yes, you can do that, okay? I hope. Do you have any questions? Okay. So, sorry.
What other rules were shown to be Turing complete?
From the famous ones, Game of Life, which is not one of these rules, just 110. If you are asking within these 88 unique rules, there's only one that was shown, as far as I know, that's Turing complete. And there's only the other one that is possibly Turing complete, which is 54. There are no other rules. So I'm coming to that point. So, Nature 1984 covered. Cellular Automata, Stephen Wolfram writing Cellular Automata as models of complexity. Okay? So, he's very happy about it. And as you can see, he says that there are 4 classes of rules. from his experiments, he decides that there are 4 possibilities. Spatially homogeneous state, going to spatially homogeneous states, like as you can see, this is not a printer mark, it's actually an initial state. So, and it dies off, just like rule 0, right? Then there are this sequence of simple, stable, or periodic structures, okay? Then there are chaotic aperiodic behavior, like this one. But you know, even with chaos, there are things that are super chaotic. I don't know what they call it, but let me tell you this. Can you find what is going to happen here with less calculation than rule 90? This is rule 90. Okay, let me show you. Let's go to rule 90 and I will tell you what I mean. Let's go to rule 90, start with 20 cells. I want to demonstrate you something. First of all, if you run it like this, this is what you get, okay? Can you find what's going to happen over here without doing this calculation? Yes, you can. How? I should have come prepared for this, but
In the middle line, it's going to be just a white line, I think.
no, it's actually coming back. Let me show you. If I go to, let's say, 40 and 20, oh, yeah, it's a white line. Yes, you are actually right. You are actually right. Why there is a white line, I can explain it. Let me show you. Look, if I start from here, 0, 0, and go diagonally, these 2 zeros actually decide what's going to happen here. No matter what happens in between. It's amazing. Look, I have zeros everywhere else, and they are diagonally converging to the middle. And Alper, you are right. The middle is always 0 because 0, 0 gives. So, for example, 0, 1, do you see diagonally going here? I get 1. And this is true for everything. I have 0, 1, I get 0, 1. Are you with me?
Yeah.
Yes? And how about 1, 1? 1, 1 goes to 0 as well. So what kind of rule is this? XOR? 1, 1 goes to 0, 0, 0 goes to 0, 1, 0, and 0, 1 goes to 1. Is it XOR? Okay, let's Google it. Yes, it's XOR. Okay? So we have XOR gates, and even if I start with randomness, look. Stay with me, please. Yes, random initial condition, right? But let me decide what this is going to be. Let's say I didn't know it, okay? I go all the way back. Look, over here, 1, 0. Over here, 1, 0. So even though it seems to be chaotic, the fate of this one is decided by the cell over here and the cell over there. So rule 90 seems to be chaotic, but it's computationally reducible. Yes? I can, if you give me this information and ask me what's going to happen here, I can just draw a diagonal downstairs and I will tell you what that state is going to be, no matter what happens in the middle. Okay? So the chaos that rule 90 has is inherited from the initial condition only. Okay? With me? Without me? Yes. Okay. But rule 30 is not like that. In the rule 30, you have these mixings. All right. So chaotic aperiodic behavior, and I already mentioned that even that chaos has levels, right? But then there is this class 4 that Wolfram really, really likes and everyone else likes. Class 4 is this complicated localized structures propagating. So in a way, you can think of it like this. Again, coming back to some recurring themes in this course, there is static depth, there is dynamic depth. In between, there is class 4, which is lifelike structures, right? That are interacting in a complicated way. Alrighty. I think we can watch a video now, just to have. What's the difference between class 4 and class 3? The difference is that in the class 4, you can perform computation. It is lifelike. I mean, there are class 3 is like gas atoms in this room. They are just bumping into each other pointlessly, right? Class 4 is like you. You came to this class, you have a pencil, you are playing with it. Lifelike automata, okay? Did I answer your question or not? I didn't. Ask it again, please.
There are two codes, so I'm
Two codes, it's the same code.
one of them is basic, one of them is widgets.
Yes, okay, let me explain. One of them is widget because I want to zoom. The other one is widget because I want to play it like this without zooming. That's it. But they are the same code. Any other questions? Okay. So, let me tell you what we are going to watch. We are going to watch John Conway describing his own game of life. Okay? Let me stop